All right, this is the practice exam for Unit 3. Question 1, we're going to use the exponential rule for differentiation. So y prime is just going to be 5e to the 2x squared, and then we multiply it by the derivative of that exponent. And the derivative of 2x squared is 4x, and the 4x and the 5 can multiply for 20x e to the 2x squared. Now for question 2, a couple of different ways we can try this one. I do always though recommend that before you take a derivative of a natural log, you expand the natural log as much as you can. So this is natural log of 3 times x to the 4th, and whenever you're multiplying terms inside of a logarithm, you can separate that into multiple logarithms. And then with this one, we can use the power rule to bring that exponent down in front. And then we take a derivative of that expansion. The derivative of natural log of 3, you got to remember natural log of 3 is just a number, and the derivative of a number is 0. And then the derivative of natural log of x is 1 over x. So it's 4 times 1 over x, which is 4 over x. Question 3, we're going to have to use the quotient rule. So it's the bottom function times the derivative of the top function. Now the derivative of the top function, that's going to be e to the 5x cubed multiplied by the derivative of that exponent, so 15 minus the top function multiplied by the derivative of the bottom function, so that's going to be 20 x to the 4th all over bottom function squared. Now we need to clean up that numerator. So what I'm going to do is distribute into that parenthesis and then combine those two terms right there. So we're going to have 15x squared multiplied with the 4x to the 5th. That's going to be 60 x to the 7th times e to the 5x cubed, and then I'm going to multiply this to that 1, so that's going to be 15x squared times e to the 5x cubed. And then multiplying there, we can get minus 20x to the 4th times e to the 5x cubed all over our denominator squared. That'd actually be okay if you left it like that. If you did want to go one step further in the numerator, if you look at each term in the numerator and figure out what they have in common, you could factor out a 5x squared and then an e to the 5x cubed. If you did that, that's going to leave 12x to the 5th plus 3 minus 4x squared all over the denominator squared. I'd accept either one of those answers right there, though. Question number 4 is definitely one, much like we did here in question 2. We're going to expand this natural log. So first I'm going to move that 5 in front and write it as 5 times the natural log of x to the 4th over that denominator. And then we can further expand that and use a subtraction sign. So still haven't taken any derivative yet, just expanding a logarithm. And then I'm going to go ahead and bring that power down in front and multiply with that 5. So we have 20 natural log of x minus 5 times the natural log 5x to the 3rd plus 1. So I've expanded that natural logarithm expression as far as it'll go. Now we can do a derivative of this first term. The 20 is just a coefficient, and then the derivative of natural log of x is 1 over x. Now the derivative of that term, the 5 is just a coefficient, and then the derivative of natural log of 5x cubed plus 1 is 1 over 5x cubed plus 1 multiplied by the derivative of 5x cubed plus 1, which is 15x squared. And then the 15 here multiplied by the 5 there is going to be 75x squared over 5x cubed plus 1. Now from time to time, this is something we've talked about in class, from time to time I see students try to simplify like that x squared with that x cubed, or I'll see somebody try to simplify that 75 with the 5, but this 5x cubed plus 1 is one term. It's got to stay together. You can't simplify a part of that term with that factor there. That just doesn't work. So that's as far as that one's going to go. Now with question 5 here, we need to use the product rule. If you want to think, for example, that's f times g, then the derivative, remember the product rule, is f prime times g plus g prime times f, and that's what we got to do here. Just follow that product rule. So y prime is going to be f prime. That's the derivative of that first factor there, so that's going to be e to the 5x cubed times the derivative of 5x cubed, which is 15x squared. So that's f prime times g plus g prime. Now g prime is the derivative of that factor, so that's 4x cubed times f, or e to the 5x cubed. So I'm going to go ahead and multiply this into the parenthesis there. So that's going to be 15 x to the 6 times e let's write this a little better, times e to the 5x cubed minus, now multiply it with a 2, we're going to get 30 x squared e to the 5x cubed plus, and then just add that term there, 4x cubed e to the 5x cubed. And then I'd accept this for 4 points if you wanted to factor out, though, a common factor between each of these three terms there. They each have an x squared and an e to the 5x cubed. If you wanted to factor that out, you'd be left with 15x to the 4th minus 30 plus 4x. For number 6, again, this is like number 4, where we're going to rewrite this a little bit. So first of all, natural log of x squared plus 2 to the power of 1/3. Then I'm going to bring that power of 1/3 down there in front of that logarithm. So I'm going to call this y equals 1/3 times the natural log of x squared plus 2. Now we can take a derivative, because that's about as far simplified as we can take that expression. So the 1/3 stays as a coefficient, and then the derivative of natural log of x squared over 2 is 1. Sorry, the derivative of natural log of x squared plus 2 is 1 over x squared plus 2 multiplied by the derivative of x squared plus 2, which is 2x. This becomes 2x for 3 times x squared plus 2. Okay, so find the equation of a line tangent. So we need a tangent line. A tangent line is going to come from f prime of x, so we need to find the derivative. And then slope-intercept form, remember, is y equals mx plus b. So first step here is to find the derivative. Now the derivative of e to a power is e to that power multiplied by the derivative of that power, and the derivative of x minus 2 is 1. So the derivative is just e to the x minus 2. Now at the point 3 comma e, f prime of x becomes f prime of 3. We just need to plug in the x value there. So f prime of 3 equals e to the 3 minus 2, which is e to the first power, which is just e. So that's our slope. When you plug an x value into our derivative, you get a slope at that x value, slope of the tangent line. So when we want, so we already had slope. So now we want the equation for the tangent line. It's going to be y equals mx plus b. We know the m value we just found, that was our value right here. So that's going to be e. And then we can multiply that with the x value of the point we're using, which is 3. And then that e there could be our y value. And then we could solve that for the missing y-intercept b. So we have e equals 3e plus b. If you subtract 3e, 1e minus 3e is negative 2e equals b. Therefore, y equals, our slope is e, and then our b value was minus 2b, minus 2e. Okay, question 8. I was able to answer a lot of good questions about this one in class. Most of them revolved around this part right here. Before remember the last page where we did question 2 and question 4 and question 6. Many times before you take a derivative of a natural log, you're going to want to expand that natural log. That's exactly what's happening here, because this is 2x squared times y to the third. So we can separate that into different expressions there. And then we can keep going and expand this one into natural log of 2 plus natural log of x squared. And then we can actually move that 3 down in front and call that 3 times natural log of y. And then we could actually move that 2 down in front and get natural log of 2 plus 2 natural log of x plus 3 natural log of y equals, and then over here we've got what we started with. Now once we've expanded all the logarithms as far as we can go is when I would take a derivative of each term one at a time. So the derivative of that first term is 12x squared. The derivative of 2 is 0. The derivative of natural log of 2 is 0, because natural log of 2 is just a number. The derivative of 2 times natural log of x is 2 times 1 over x. And then the derivative of 3 times natural log of x is 3 times 1 over y times dy dx. I'm going to subtract this 2 over x to the other side because it doesn't have a dy dx, so 12x squared minus 2 over x equals 3 over y times dy dx. Now I need to get dy dx by itself, and it's being multiplied by 3 over y. So if I multiplied this side by y over 3, then I can cancel that. And then I would multiply this side by y over 3. So we have y over 3 times 12x squared minus 2 over x equals dy dx. Now, question number 9 is a bit of a tricky one. Specifically because of that term right there. Now, here's one way you could think about this. The derivative of e to some power is e to that power multiplied by the derivative of that power. Now the problem is that power is a product, so you'd have to use the product rule. F prime times g plus g prime, and because that's implicit differentiation, we need dy dx, so there's g prime times f. And then we could do the derivative of the other side, which is e to x. And since this was the way that was shown in the solutions that were written out, I'm just going to stick with this way. There is a typo on the solution sheet I sent out originally. This, I think, said y cubed. Now, where the 15 came from is we got 3y squared times 5x, so that's going to be 15x y squared dy dx, and then just multiplying that and that, we're also going to have a e to the 5x y cubed attached to that one, and then here we're going to have a 5y cubed e to the 5xy cubed. Now that's the only term there with the dy dx, so I'm going to move this term to that side by subtracting. So we're going to have 15xy squared e to the 5xy cubed times dy dx equals 8x minus 5y cubed e to the 5xy cubed. And then, since that's multiplying there, I just need to divide by that term. So the dy dx, this right there becomes the numerator. So and that there becomes the denominator. All right, for number 10, we talked about this one in class a little earlier. The key phrase here is that it's growing at a rate proportional to its population. So when you see a phrase like that where it's growing or decreasing at a rate, you need to remember it's going to be using that formula, where y is a future amount, c is an initial amount, k is a relative growth rate, and t is time. Now, they didn't give us relative growth rate, k, so we need to use a value for y, c, and t in order to solve for k. To answer the actual question is, what will the population 6.7 years from now be? So that's a future amount. So that means ultimately we're trying to find a value for y. But in order to do that, we need to figure out what that value for k is. So there was some discussion in class regarding this right here, the current population and this value of c. C is just an initial amount at time t equals 0. So I'm actually going to use this phrase 6.3 years ago and call that time t equals 0, which means this is actually our initial amount. So if I use 1,312 as the initial amount, and then in 6.3 years, according to this, that amount is going to turn into 1,964. So if I divide, then we have that, and taking a natural log on both sides, natural log and the e are going to cancel out. So the natural log equals k times 6.3, then divide by 6.3. And then we can get an approximate value for k. So this is where you would get your calculator and probably do this a step at a time and divide inside that natural log first. So if we did 1,964 by 1,312, and then put that inside a natural log, and then divided that by 6.3, we're going to get 0.064. So now that we have that growth rate, we can answer this question: what will the population 6.7 years from now? And now, meaning that we have a population of 1,964. So I'm going to use that now as our initial value. So the current population is going to be, sorry, the future population there, y, is going to be the current population, 1,964 times e to the 0.064, and then in 6.7 years. So again, trying to chunk that down, I'd probably multiply those together first. So 0.064, multiply that by 6.7, and then raise e to that power, and then multiply that by 1,964, and we get roughly 3,016. Now there's going to be an allowance of a variance here, just depending on how much you round that decimal and how much you round here. There's going to be some rounding going on. I understand that. So if you're within 315, 314, 317, somewhere in that ballpark, you're going to be fine. So I wouldn't worry too much about that. So, and they didn't say whether this was a population of people or animals, so we don't really need to label that with any kind of unit, just 3016. Now the first partial derivatives, that implies all of the partial derivatives. So we need to find the partial derivative in the direction of x of our function, and we need to find the partial derivative in the direction of y. So first of all, in the direction of x, this means that y is not a variable. Y is representing just a number, so it's a constant really. So looking at this first term, rather than 3 being a coefficient of x, you need to consider 3y squared is a coefficient of x. And then if you take the derivative, that just becomes 3y squared. Next term, the 5 and the y are coefficients. That's just going to stay coefficients. And then the derivative of x squared is 2x. So the 2 would multiply with the 5 and make 10xy. Next term's easy. It's 14x. Now the derivative of 5y, since y is just a constant, the derivative of a constant is 0. Now for this one, we're taking the derivative of pretty much here just y squared, which is 2y. The 2 would multiply with the 3 to make 6, so it's 6xy. And then for this next term, we're pretty much just taking the derivative of y, and the derivative of y is just 1, so that's 5x squared times 1, which is 5x squared. Now the derivative of 7x squared, where 7x squared is a constant, the derivative of constant is 0, so that term becomes 0, and then the derivative of 5y is 5. This is going to be the product rule primarily, then with a little bit of a chain rule there going on. So if we want to think about that as f and g, then the product rule says f prime, which is going to be 5x to the 4th times g plus g prime Now this is where we're going to have a chain rule. Now the derivative of that inside function is 15x squared. So this whole thing right there would be g prime, and then we need to multiply that by f. Now we just need to simplify as much as we can. The 2 and the 15, I'm going to multiply those together to make 30. Now looking at what they both have in common, they have a 5 in common there. So I'm going to factor that out, and then they have an x squared in common there. I'm going to factor that out, and then they have at least one 5x cubed minus 4. I'm going to factor one of those out. That's my common factor. That factored out of that leaves an x squared. And then that factored out of one of those leaves one of them, 5x cubed minus 4. 5x squared factored out of 30x squared leaves us 6. And then that was factored out from that, leaving that term there in parentheses. So then multiplying together here would give 5x to the 5th minus 4x squared plus 6x to the 5th plus 30 . So then we would have 11x to the 5th minus 4x squared plus 30. So we've got a question here. At what rate is water being poured into the cup? So if water is being poured into a cup, that's changing the volume. The volume's going up, or the volume's increasing. So they're asking really at what rate is the volume increasing? So if the volume's increasing, obviously it's changing. They're asking for the rate of change. Another way of saying rate of change is derivative. So they're asking to find dV, or the rate of change of the volume. But a derivative has to be with respect to a variable. And you can tell that the variable is time because the given rate is in meters per second. So it's dV over dt. When, now they've given us a rate right here. And that rate has to do with water level or height. So I'm not going to say that h equals 2 because it's a rate of change. I'm going to say it's dh with respect to time. So dh over dt equals 2 centimeters, and specifically when the water level itself, so that's the height, equals 8 centimeters. So really all we got to do is find the derivative of the volume. So dv dt equals pi, and then just as a little side note here, pi times 1/3 h cubed. Instead of having h cubed over 3, you might want to think of it as 1/3 h cubed. Because when you take the derivative, the 3 and the 1/3 are going to multiply together, canceling out. So you've got h squared. And then this is where you need to remember related rates is implicit differentiation, because we're taking the derivative with respect to time of h. So since the variables don't match, we need a dh dt. So we just need to plug in the values then. The height is 8, and dh over dt was 2 centimeters per second. So this is pi, and 64 times 2 is 128, so I'm actually going to write that as 128 pi. And then since this is a volume, it's centimeters cubed per second. Okay, for part A, the intervals in which the function is increasing or decreasing and the relative extrema all come from the first derivative. And then you set the derivative equal to 0. So I'm going to factor out a 3 first. that equal to 0. Now, looks like it's not going to factor, so unfortunately we need to use the quadratic formula. Once you get to this point, you would find out what the square root of 12 is. I'll get my calculator out here. So the square root of 12 is about 3.46. So then I would add that to 4 and then divide it by 2. So we get 3.73. For one of them, and then 4 minus the square root of 12, so that's going to be 4 minus square root of 12. That's 0.53, and then divide that by 2, and that's about 0.28. So those are the two critical numbers. Once you've got those, they're placed on a number line. And then we test values in all the intervals. So we could test 0, we could test 3, and we could test 5. These are all numbers in each of those intervals. If I plug in a 0 into the derivative right there, I'm going to get 0 minus 0 plus 1. That's 1, and then 1 times 3 is 3, so that's positive. If I test a 3 right there into the derivative, I'm going to get 3 squared, which is 9. 9 minus 12, which is negative 3. Negative 3 plus 1 is negative 2. Negative 2 times 3 is negative 6. So that's negative. If I plug in a 5 here, I'm going to get 5 squared is 25. 25 minus 4 times 5 is 20. 25 minus 20 5 plus 1 is 6. 6 times 3 is 18, so that's positive. So it's positive up until here, negative up until there, and the positive. So what that tells me, it's increasing from negative infinity to 0.28, and it's increasing from 3.73 to infinity. It's decreasing from 0.28 to 3.73. This question also asks for the relative max and min, the relative extrema. So there's a relative max when there's an x value of 0.28, and there's a relative min when there's an x value of 3.73. Now what we need to do is plug those in to a calculator here and find out what those are in the original function. So if you plug in, let's go with the 0.28. So 0.28 cubed, and then minus 6 times 0.28. We're going to square that, and then plus 3 times 0.28 plus 10. That's about 10.4. And then doing the same thing for, what is that, 3.73. So going back, so 3.73 cubed minus 6 times 3.73 squared plus 3 times 3.73. So that's about negative 10.4. Okay, for part B, it wants, what does it want? It wants to determine intervals at which the function is concave up or down and inflection points. So concavity is from the second derivative. So let me write the first derivative. We had 3x squared. So if y prime was 3x squared minus 12x, I think it was plus 3, yeah. Then the second derivative would be 6x minus 12. If you set that equal to 0, you're going to get x equals 2 as the critical number of the second derivative. So if I test something like 0 and positive 4 for my test values, if I plug in a 0, I'm going to get 0 minus 12, which is negative. If I test a positive 4, I'm going to get 24 minus 12, which is positive. So I know that the graph is concave down. According to that graphic, it's concave down from negative infinity to 2. Concave up from 2 to infinity. And because there's a switch in concavity, there's an inflection point with an x value of 2. And then I need to go to the original function and find out where that is. Now I could plug in 2 into here, run it through, but I notice right here, if I plug in a 2 right there, I get 2 minus 2, which is 0, and 0 times all the rest of that is 0, so I know that it's going to be 2 comma 0. Okay, so sketch the graph. We need to find all the intercepts. So the y-intercept comes from letting all the x's equal 0, so I know the y-intercept is going to be 10. The x-intercept are found from the factored form there, which is why that's provided. All that really is there for is to give you the x-intercept, so I know there's one at negative 1, positive 2, and positive 5. And then my relative extrema, 0.28, comma 10.4. So yeah, that's right about there. And then negative 10.4, so 3.73, negative 10.4.